Alright, Lesson 7.2, we're going to take what we learned in Lesson 7.1 about proportions and ratios, and we're going to apply that to all the things we just learned in Chapter 6, the different polygons and parallelograms and shapes and things like that. So we'll be exploring kind of a new area that we haven't talked about before called similarity. And I'm sure you've heard this term similar before. When two things are similar, they're kind of alike, but not exactly the same. And that's kind of how they're used in geometry as well, but there's a very specific definition that goes along with it. In geometry, when we say that figures are similar, they have the same shape, but a different size. So it says two polygons are similar if corresponding angles are congruent and corresponding sides are proportional, meaning if we take, one side from the first figure and one side from the second figure and we look at their ratio, let's say the ratio is 2, then that means that every side in the second figure has to be twice as large as each side in the first figure. So we'll see this as we get to the examples, but it's a very important part of similarity is this idea of proportional sides. And, there's lots of similar figures out there that we run into. Every single square is similar, right? Because they all have 90-degree angles, and because all of their sides are congruent, then we know that, any two squares will always be similar. The same thing with equilateral triangles, right? Equilateral triangles will always have the same angles, and because their sides are all the same, they'll always be proportional to other equilateral triangles in terms of their corresponding sides. So lots of similar figures out there. And I said there's going to be a lot of parallels here between similarity and congruency, and another one is the symbol that we use. So if we look at the symbol for congruent, it's essentially an equal sign with a little squiggly above it. Well, if we take that symbol and we take away the equal sign, we're left with the symbol for similarity, which is just the little wavy line on the top. That's how I remember it, right? If you take congruent and you take away the equals, meaning they're not exactly equal to each other, they're just kind of alike, you're left with this little squiggly line. Now, to draw another comparison between congruency and similarity, we're going to, just like we wrote the congruency statements back when we first learned about things being congruent. So if we head to our figure here, we can see that we have two triangles which are congruent, right? A, B, C is going to be congruent to E, F, G. And I kind of color-coded the sides there for you. So from this, we can make a number of conclusions just based on this congruency statement that triangle ABC is congruent to triangle EFG. We can take the first two letters, right, and so we see this corresponding side of AB, and we can say that that's going to be congruent to these first two letters, that corresponding side of EF. So AB is congruent to EF, and then continue around BC to FG, and CA to GE, all of those things being congruent when we have two congruent triangles. We also have the angles, right? Angle A and angle E. Right? Angle A corresponds to angle E, so the two of them are congruent as well. B and F, C and G. So we've got all these things that we can conclude just based on the congruency statement. If we were to instead write this as a similarity. So here we can see two similar triangles, right? A, B, C, and again EFG, and we have our statement up here. Fix that a little bit. We have our statement up here. ABC is similar to EFG. See, there's that similar figure, the little squiggly line. And just like in congruent statements, that means that all of the corresponding angles are congruent. So angle A is going to be congruent to angle E, and B and F and C and G and so on. All of those are congruent. But if I were to try to say that side AB is congruent to side EF, well, that would just not be true, right? We can see definitely that triangle ABC is much bigger than triangle EFG. So those sides are not going to be congruent. They're not going to be the same. But we can put a little squiggly line here and say that AB is similar to EF, or basically that they're proportional, and that would be correct. So when we look at these corresponding sides, we can say that they are similar, and therefore they will be proportional, which is going to be very important for a number of the practice problems that we will get into shortly. So, making our way back to the notes, whenever we look at those proportional sides, we can come up with what they call a similarity ratio, which is basically just going to be the ratio of the lengths of the corresponding sides of similar figures. Like I mentioned before, if you have two squares that are similar, and the length of the side of one square is twice as large as one of the lengths of the other square, then we know that all of those squares are going to have that same relationship, right? So their length will be twice as big as the corresponding side of the other square. And it works for things that aren't squares as well, as long as we can say that they are similar. Now, this is going to tie in quite a bit to art and architecture and design and things like that with something that we call the golden ratio. So when looking at shapes and figures and things like that, there's something that they call the golden ratio. And they give a value to it, right? It's 1.618 to 1 is the golden ratio, right? It's just this kind of special ratio that we see popping up all over the place. Now, people who are more familiar with it know that it has been coming up for centuries. So ruins in ancient Roman ruins, they find this ratio, this golden ratio, when they look at the pillars as compared to the distances between the pillars, and the sizes of the windows have this ratio, and all these things in architecture and design. And even in art, if you look at the Mona Lisa and you look at things like length of the nose and width of the brow and distance between the eyes and like all these different things, you can compare the values in there, and you see this ratio pop up more and more often. And it's found to be very visually appealing, right? People, when you use this ratio in design and art and things like that, people tend to enjoy it. It looks like it is supposed to, I guess is what they say. So we'll see this quite a bit, and we'll do some hands-on stuff with it as well as we continue on. And then, so a golden rectangle is just a rectangle that can be divided into a square that is similar to the original rectangle. And so if you look at the figure that I just threw in there, that is an image of a golden rectangle, and you can see that you've got the larger rectangle, or the largest, the whole figure is a rectangle. But then as you draw the line, you've now created a square on the left, but then you're left over with that area on the right that has all the shapes inside of it, which is a rectangle that is similar to the original rectangle. And then we can do it over again, right? You cut it into a square, and what you're left with is another similar rectangle, and then take that rectangle and cut a square off of it. You're left with yet again another similar rectangle, and on and on and on. So those rectangles are kind of neat in that you can just keep going and going and going, but we do see this ratio pop up quite a bit, and so we'll do some fun stuff with it as we continue on. Now, looking at the first example, they've essentially given us a similarity statement between two triangles ABC and XYZ, and I want to caution you to be very careful to pay attention to the similarity statement, not just look at the figure. In this case, we're okay. Notice how the shapes are laid out in a similar fashion, and A does correspond to X, and B does correspond to Y, and C does correspond to Z. But they could just as easily have, here, let's take a picture of ABC. They could have taken this image, ABC, and we could, rotate it around. We could have it upside down, right? Throw that in there. And then notice now we don't have, B corresponding to X and A corresponding to Z and C corresponding to Y. They're in a different order. And I know it's a little more obvious because of this shape, but I just want to caution you to be very careful with that. Don't just assume that because they look like they're in the same places that those are corresponding sides or angles. Okay? Always look back to this similarity statement and see that A corresponds to X, B corresponds to Y, C corresponds to Z, so that you don't get into any trouble. Now, once we look at this, they're asking us, well, based on this statement, the measure of angle B is going to be equal to what? Well, we can see we don't have any values in here in our triangle ABC, so we're going to have to go and look over here. We can see that we've got two angles here, and that B does correspond to Y, right? Based on the similarity statement, B and Y are corresponding angles. Therefore, if we know that Y is 78, we can conclude that B must also be 78. Then we can move on and use the statement again to look at a side. Now it's asking us to set up this proportion here, and they give us BC and YZ. So BC is over here, YZ is over here, and it's saying that that's going to be proportional to some side over XZ. Well, here's XZ, so basically we want to find the side on triangle ABC that corresponds to side XZ. So if we see XZ is the first letter and the last letter, we can just come over here and say, well, AC would be the first letter and the last letter here, and so it's going to be side AC. We can throw that in there to complete the proportion. The next quick check problem is pretty straightforward. Again, essentially just doing what we did in that example, but finding a different angle and a different proportion between sides. As we look at this next figure, the next example, they're asking us to determine similarity. So they're looking at these two parallelograms and they want us to determine whether or not they're similar. Now, the book goes through quite a bit of work and then comes to the correct answer. I would say this problem doesn't necessarily require work. If they ask us to determine if they're similar and we can see right away that this angle is 120 and this angle is 100, well then we should be able to fairly quickly conclude that these are not similar. We could go one step further and say, okay, well if this is 120, this is 60, and if this is 100, this is 80, so then we can be doubly sure that none of those angles in those two shapes are the same. Remember, sides are going to be proportional in similar figures, but the angles must be congruent. So we don't even need to do any work to say the angles are off, therefore this whole thing is not congruent, right? They're not similar because the corresponding angles are not congruent. But the book goes ahead and does this in a little more of a formulaic approach. They look at the sides first instead of the angles. So if we come to our sides, we can see, they're going to take AB and compare it to KJ, and then BC and KL, CD and LM, DA and MJ. And we can see that when we throw in values for all of these, we end up getting 2 over 4, 1 half, 2 over 4, 1 half, which all simplify down to 1 half. So that means that the proportion, or the ratio between the sides of these are all proportional, right, for the two parallelograms. But that's not the only requirement for similarity. Just because all the sides are proportional does not mean that the two are similar. We do have to check the angles as well, and as we mentioned earlier, they're not congruent. And so even though all of the corresponding sides are proportional, the parallelograms themselves are not similar since the angles are not congruent. We've gone to the next example. As we look here, they give us another similarity statement, and they want us to find the value of x, right? X is representing the length of that side AC. And so we can set up a proportion just making sure that we include this side AC in our proportion. So AC, we can tell from the similarity statement, is going to correspond to YZ. So we can say AC over YZ. And then we just want to pick the sides, the corresponding sides that are left that have values for them. If we were to pick AB for the other side of this, well, there's no value for AB, so we'd introduce another variable. But if we choose BC and XZ, then there's values for both of those sides, so that would be the better of the two, right? We know that those are proportional, so the ratio between those two should be equal to the ratio between those two. And then we can plug in what we do know, right? We know that BC is 12, XZ is 40. We know that YZ is YZ is 50, and then AC, that's what we're looking for, so that'll be our X. From here, you could cross multiply and then divide by 40 to get your answer, but really the quicker way would be just to multiply both sides by 50. So you're going to multiply both sides by 50, it cancels on the left, and you just get 12 over 40 times 50, which is 15. So really just setting up a proportion like we did yesterday, but using the knowledge that these shapes are similar, and so the proportion of this side, which corresponds to this side, should be equal to the ratio of this side, which corresponds to this side. All right, and then one last example problem before I set you loose on the quick checks. We can see we're going to be using the golden ratio, so we could look back into our notes to remind ourselves that the ratio is 1.61 to 8, although they do give it to us right here as well, so we probably don't need to go back in our notes. It says the dimensions of a rectangular tabletop are in the golden ratio. The shorter side is 40, find the longer side. And they tell you to let L represent the longer side. So we're going to write our proportion, which means we're going to use our golden ratio, which is 1.618 to 1. And on the other side, we're going to use our two sides, L being the longer side over 40, which is the shorter side. Now, we're using the golden ratio here. The question is, I can not hear, but imagine some people asking, well, how do you know that this is L over 40 instead of 40 over L? Or 1 over 1.618, or sorry, 1.618 over 1 instead of the other way around. This is how I would set it up, right? We know that we want to solve for L. So the best thing to do is have L in the numerator, right? When you solve for something, you want it to be in the numerator. So let's put L in the numerator, which means 40 must be in the denominator. Now, how do we know that it's 1.618 over 1 instead of 1 over 1.618? Well, if we look, 40 is the shorter side, L is the longer side. So when we write this, if we have the longer over the shorter, then over here it needs to be the longer over the shorter. Right? So 1.618 would be longer than just 1. So that's how I would keep it in line in my head, is that we have longer over shorter here, so we need to have longer over shorter here. Essentially, we can cross multiply, right? Cross product, and L times 1, that makes it easy for us. We just get L, and 40 times 1.618 is 64.72. So if we're rounding, it's about 65 inches for the second side of that tabletop. The quick check's fairly straightforward. Again, they follow directly the examples that we just completed, so if you have any trouble, look back to the example and try to model the work that they have done. All right, and we will pick up from there when I return.